So tell us about the machine and when it was built, who built it, and how it works.
This machine is a single adaptive neuron. So you talk about machine learning, this is the most elemental machine that learns. It's right here. This was built in 1960. We call it ADALINE, an adaptive linear neuron. The circuits inside were designed by Ted Hoff. It's a more compact version of the earliest thing we did that Friday afternoon in 1959. So this is really, all the technology is 1959, but the actual box was built in 1960. It took a while before we got technicians and, before we can put it all together. Now, we're able, with these switches, to put in input patterns. For example, here's the pattern X. We'll put in another pattern. I'm going to play with these patterns. That's a T. And no, if you can see that all right? Is that okay?
Yep.
All right, now, whoop, that's the T. See, I need to look at that to see whether I goofed up here, because looking at these switches, it's hard to see which way they're set. All right, we'll put them all down. So this switch provides input to that weight, this switch to that weight, this switch to that weight. What the meter is reading is the sum. So take this, whatever the value that is, and multiply it by whatever value this is, plus whatever value this is, multiplied by that, and this by that, and this by that. Oh, look at this one. That's a bias weight. Its input is as if it has a switch that's always up. You can't control the input to that. Okay, now with a switch up, the input to that weight is +1. Down is -1. So it's binary. So we're able to put in binary patterns. The binary here is +1, -1, not the usual binary 1 and 0. If we put this in, here's +1. Now you're going to take this and multiply by that weight. I set it to 0. But if you do that, you can see they're going up. They go back to 0, and then go the other way. See? And then we put in some crazy stuff. See, it's forming a sum. All right, now what I'll do is I'll put these all down to start with. I'm going to reset these. You don't have to do it. You can train it from there. It's just a little more predictable how many times I'm going to have to fiddle with this. We put them all 0. But it's not critical. Okay, good enough. Now, I'm going to put in an X pattern, like that. That's an X pattern. I'm going to train it for an X pattern to give a positive response, a +1 output. So this is positive, so I want to make the meter go that way. This is positive, so I go positive. Negative. Negative, I go negative. Positive. positive, negative, positive, positive, negative, negative, positive, positive, negative, positive, negative, negative, positive.
How do you know how much to turn the dial?
I know this machine. I know how many clicks, depending on how big. See, the error is the difference between what the needle is reading and what you want it to read. What you want it to read is the desired response. So I desire for this input pattern to train it to give a plus response. So we're training it. So that's the T pattern. If you look at the weights, you can actually see the T pattern in the weights. And that's the last time you're going to see anything in the weights. You can see the pattern, anything in the pattern and the weights related to the patterns of the inputs. They're going to get all scrambled up. Now we put this so there's a T pattern, and let's say we wish the T pattern to be negative. What that means is that wherever the switch is up positive, to make that go more negative, you make this go the opposite. So if this is positive, you make that go negative. Now watch. I have further to go. Bigger error. And this is positive, so we go negative. Positive, we go negative. Positive, we go negative. Positive, we go negative. Negative, we go positive. Positive, we go negative. Positive, we go negative. Negative, we go positive. Negative, we go positive. Positive, we go negative. Positive, we go negative. Negative, we go positive. Negative, we go positive. Positive, we go negative. Positive, negative, negative, positive. So we're getting a strong response for the T. Negative is what we wanted. Now let's put back the X. X is positive, and T is negative, so it separates the two. We trained it. The response to the X has been hurt by adapting on the T. Every time you train in something new, you're changing the weights, so you're disturbing the responses that you had trained in already. But if you say, never mind the weather boys, everything is going to be fine, just keep on doing it, and pretty soon you're going to get what you want with any input pattern. Magic. Okay, now let's put in another pattern. How about a C pattern? And let's say we want to make that positive. Well, it's a strong negative. Boy, we have a way to go. So I'll give it, this is positive, so it go positive, positive to positive. So I went 6, now I'll go 7. See, it's got a long way to go. This is negative, so we go negative. This negative, negative, positive, positive, negative, 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 positive, positive. Ooh, look at that strong response. So this strong response to the C, I'm going to put in another pattern, a J. See that J pattern? I'm going to make that come negative, and it's a little bit positive, so I'm going to go four clicks. So that's minus, so we go plus. Minus, we go plus. Minus, we go plus. Plus, we go minus. Plus, we go minus. Plus, we go minus. Minus, we go plus. Minus, we go plus. Minus, we go plus. Plus, we go minus. Minus, we go plus. Minus, we go plus. Plus, we go minus. Plus, we go minus. Okay, so there's the J. Here's the original T. I'm sorry, that's wrong. Here's the original X. It's supposed to be plus, it's reading negative. So we're going to have to train it. Well, let's just go through, I'll show you. This is the X.
Oh, I'm sorry.
You saw the X is in trouble. And this is the T, which is supposed to be minus. And that's in trouble. And here's the C. We got a good strong response to it. So the C is fine. Oop. There's the J. That's fine. So the C and the J are fine now. Okay, now we'll put in the X like before. And we got, we're going to make that plus. So that's plus. Can't go any further. We hit saturation, don't worry about it. Minus. Minus. Plus. Plus. Minus. Plus. Plus. Minus. Minus. Plus. Plus. Minus. Plus. Minus. So the X is now trained in pretty solid. And let's put in the T. Oh, that's bad. So we got to go, we want that to be -1. T is -1. X, T, C, J. X is plus, T is minus, C is plus, J is minus. So here's the T, should be minus. So this is plus, and we got a long way to go to it. Hope we can't go anymore. Minus, we go plus. What, did I do that right? Yeah, minus. We go, that's right. Plus, we go minus. Plus, we go minus. Minus, we go plus. Minus, we go plus. Plus, we go minus. Plus, we go minus. Let's see, we're here. And that's a minus, so we go plus. Minus, we go plus. Plus, we go minus. Can't go anymore. Saturated. So there's the T. All right, here's the X. It's positive, it's good, that's what it's supposed to be. T is supposed to be minus. C is supposed to be plus. It is. Oops. J is minus. So it's been trained. And if you look at the weights, you'll be damned if you can look at them and try to figure out how that thing is able to do that problem. So the question is, how does it do it? Well, let's hold off for a moment. I can make it as strong as I want, -1 +1, without any trouble if I keep on doing it. And it will converge and give me perfect responses if I keep training it, just wear my fingers out. Well, you've seen the ADALINE boxes, and you've seen them being trained. What I'd like to do is explain to you exactly what's going on. And the first picture I have here shows a diagram of ADALINE. So you have the circles with an arrow stand for the weights, and the arrow means variability. So we have variable weights. The input pattern is an array of input signals. Each input signal goes to a weight, and the product of the two goes into the sum. So what comes out is the sum of all these products. So it's this vector multiplied by the weight vector gives you the output sum. So this is a linear combiner. The meter is attached to the sum. So that's what you're looking at on the meter was the sum. So your input pattern vector goes here. This is the weight vector. pattern vector goes to the weights, creates a sum. You see it on the meter. Now, the weight changes I gotta get number 2. Here's number 2. What we were doing with training Adeline with LMS is that we take the pattern vector, add it to the weight vector. You add it if you want to increase the sum. You subtract it if you want to reduce the sum. So this is the weight vector, this is the pattern vector. This is the x coordinate, that's the y coordinate, this is the z coordinate. So it's x, y, z in the three-dimensional space. And we have a pattern is a vector, the weights is a vector, and we add the pattern vector to the weight vector. So this is a change in the weights. And notice that this line is parallel to that. So when we make a change in the weights, we make the change in the same direction as the pattern vector. So in other words, you add the pattern vector to the weight vector. So this is adding it, this is subtracting it. So you can go this way and increase the sum, that way and decrease the sum. So this is what's going on when you're doing the algorithm. This obeys what I call the principle of minimal disturbance. The idea is to adapt to reduce the error with minimal weight change. You want to change the weights as little as possible. Every time you put in something new that you want to train it to, you want to do it in such a way that you disturb the weights as little as you can. And this does it because by making the weight change in parallel with the pattern vector, the change in the sum is the product of this delta W vector and the P vector. So if you make this at the same angle as that, the cosine of the angle between the two is 1. And that's maximum. So you get the biggest, by going in that direction to change the sum, you're getting the biggest change in the sum for the least change in the weights. So that's the principle of minimal disturbance. And every neural net, every single one of them obeys this principle of minimal disturbance. And nobody even knows about it. Now you do. That's what makes it all work. So here's the this is the LMS algorithm. It says the next weight vector equals the present weight vector plus a constant 2 mu times the error times x. So the change, this is the change in the weights. This is the next weight vector, this is the present weight vector. This is the change that you're adapting. And the change is proportional to the error. The bigger the error, the bigger the change. As you saw, when the error was big, I had to do more clicks. And this is x. This is the input pattern. So you're taking the input pattern, multiplying it by the error, and adding it to the weight vector to get the next weight vector. And the error is the difference between the desired response and the actual output response, which is the input vector multiplied by the weight vector. So this obeys the principle of minimal disturbance, the LMS algorithm. So in other words, you're making a change in the weight vector in the direction of the input pattern vector. So you get the biggest change here for the least amount of change in the weights. Principle of minimal disturbance. And that's what makes it work. They all work with that. Years ago, I found out that the mean square error is a function of the weights. This is weight 1, this is weight 2, and this is the mean square error. It's a quadratic function. It's a paraboloid. And at the bottom of the bowl is a value, in other words, the value of this weight and that value of that weight takes you crisscross to the bottom of the bowl. If you adjust the weights, this weight and that weight, according to this, you're at the bottom of the bowl, and the mean square error is minimum. So that's the optimal set of the coefficients. So you look at it in a simpler form. This is the mean square error as a function of a single weight. And as you adjust the weight, the mean square error is a quadratic function of it. So what you do is you use the gradient to take you down to the bottom of the bowl. So here's the bowl. You start out at a certain point on the bowl, and you stop following the negative gradient down toward the bottom of the bowl. And it's not obvious that we're doing that with the LMS algorithm, but that's exactly what it does. So that concludes what I wanted to tell you about. I'm happy to be able to be here and record all this at age 94. And I thank you for your attention.